Hello everyone. So thank you very much for Professor Almito for her invitation to the spring school. And I apologize for not being able to make it in person. And however, I've been following you guys on Twitter. I've seen the pictures of my friend Mark and seen Dr. Drew and Professor Alioda. So hopefully in the near future I'll be able to see all of you guys. And it's such a pity that I won't be able to see all the audience. And I hope you can hear me well. And the topic for today will be how we can use hardware to do authentication for the Internet of Things applications. And we're now living in the era of this Internet of Things. And starting from the home we live, we call them smart homes because we have this smart sensor, smart refrigerator, and all kinds of smart things. And then you have this city, which nowadays people call the smart city, and which is powered by the so-called smart grid, where the users can also generate power. And you see these automobiles, which are called smart cars. We drive smart cars. Maybe these cars just drive by themselves. And people nowadays, we call ourselves smart me. I don't know, all these things make us smart or not, but that is the way people nowadays call ourselves. And the things behind this IoT or Internet of Things are all kinds of smart devices. And you see here the smart home, and you have a lot of these smart light bulbs, and then you see the smart lock, and all these kind of things, the keys. And behind all these things are hardware. So without hardware, we don't have all these physical devices. So that is why I wrote at the corner, hardware is the root of the Internet of Things. So we do need hardware to make all these things happen. And this is another perspective of Internet of Things. I believe it is from IBM, and then we call it Internet of Everything. And on this slide, you see the four components here, where we have people, the data, which people most likely call big data, and the things, which are the devices, and the process. And I want to emphasize a little bit more about the process. That will lead us to see why we want to do as authentication. So if you can see the screen, and it is, I'm going to read what is written here about the process. So in the process, it is written that process is the delivering of the right information to the right person or the right machine at the right time. So this 2.5 lines has 3 words called right. And how can we verify it is right? Whether the data, the information is correct, or whether the person or the machine is whatever they claim they are, and whether the time is the right time. So for all these things, we need authentication. We need to verify this. So what should we authenticate? And basically, we have to authenticate everything. Because now you have this Internet of Things, so majority of the things are not handy, and we don't have physical access, and remote from any corner you go. So you have to authenticate all these items. So this is the original figure. If you recall, it is something very similar to the very first slide, and it is come from the ST Microelectronics. In the middle of this Internet of Things, they don't have IoT here. They have actually put security. It just shows you how security is centered in IoT. And when we do authentication, we'll see, okay, so we have already a lot of these proven crypto solutions for authentication. And why it is new for IoT applications? So basically I mentioned 2 things here. So first, these crypto solutions are not practical. And a lot of small IoT devices, they are extremely resource constrained. And for the crypto solutions, we involve a lot of very, very power-hungry, computation-intensive computations. So we could not afford to do that on these small IoT devices. And second of all, for a lot of these authentications and the crypto-based solution, they were developed, most of them during World War II, and they are trying to authenticate things 100% accuracy. So basically, we convert everything from analog to digital, and then you have to authenticate every single bit. If one bit missed out, the entire thing is missed out. But for IoT devices, a lot of times we don't need it. For example, why I did my fingerprint for the UK visa, you took my fingerprint and you do the fingerprint authentication. People never do a 100% match. So if it is a 70% match, that is considered a very good match. So that is why I write overkill here. So the traditional crypto solution overkills a lot of these IoT applications. So that brings us to what will be the advantages of using hardware to provide authentications. So in most cases, hardware-based solutions will be faster, consumes less power, and then they are better trusted because they have hardware doing these things, so it is a little bit harder for the attackers to mess around with the hardware. And also, for the same reason, it can be more secure. However, the hardware-based solution, the biggest drawback is probably it cannot provide the authentication at the same level as the crypto-based solutions. That is why, the lighter means here, lighter, what we call the lightweight. So we're not talking about, you save resources. We're talking about, in this case, authentication, security you achieved is lighter than before. Okay, so now let's start with the device authentication. So this has been a research topic for ages. So starting from things which most of us know is called a serial number, and it can be physically indented on the device or stored in the computer's memory. So let's see this motherboard, and then we see two components. So first, this is a EPN module, the trusted platform module here. And you see here, these are the serial numbers. It has a barcode, it has all these numbers printed here. And also here, there's another CPU here, and you see, somehow it is upside down, and you see the letters, SLB 9635 something. So all these are the serial numbers, and they are good for authentication purposes, because people can identify which devices it is and what is the serial number. And however, this is what people call the passive ID. It don't have anything to do with the functionality of the device. You could change the name of this, change the number, but the device or this piece of components still do the same thing. And the big drawback of this is reproducible. In some sense, people can forge the ID. They can change, for example, this C to an O, with this 0, they can change it to an 8 or to a whatever number. So that brings us to something better than the serial number. So this is also something people have been doing in the past. So one thing is called integrated circuit ID or the ICID, and these are based on the silicon manufacturing variations. For example, people have been using S1 POP or the timing signatures of the device or the leakage signature of the device to authenticate, to identify the chip. And this, again, they are passive, they are non-functional, but however, it is unclonable. And I think from Dr. Gu's talk, I've learned, what unclonable is. That means, even if you know how to fabricate it, and it cannot be this identical thing as we have here, because of these fabrication variations. And finally, I'm going to mention something called digital fingerprint. So these are the things that designers casually put on the chip to make the chip distinct. And I'm going to give you a quick review, a quick history of the development of fingerprint for chip identifications. So this is the standard design flow for the ASICs or for computer chips. So you start from the system level, specify what you want to achieve, and then you design the architecture, and then you do the functional design, and then you come to this what we call logical design, where you convert everything into binary. And then you do the circuit design, you do the physical design, do the floor planning, the wiring, do the routing. So finally, you go to the fabrication, the foundries, they build a chip for you, and then they package, you test it, and then you have a working chip. So it is important here to separate from the fabrication here. So before that, on above of this, these are the things people call prefabrication. And below this is the post-fabrication. And that makes a big difference about the practicality of this, whatever techniques. So, about 20 years ago, when we first started, the intellectual property protection for hardware designs, we mentioned about the fingerprints. And there are approaches talking about how to embed fingerprints into the chip. And the key thing about this is all these approaches, they are at the pre-silicon level, before the fabrication. And theoretically, this works perfectly. They can make every design different. And they can detect the difference, they can use that difference to decide, which chip it is, and then to trace every single IP. However, the key problem here is because all these things, they have been made pre-fabrication, which means that for each chip, you have to do a different mask to fabricate it, which becomes extremely expensive. So nobody could afford to do that. So that brings us to what happened in the past couple of years. So we started developing things called post-silicon fingerprint techniques. And this, I'm going to tell you a couple of them, to give you a flavor how it can be done. And the key feature here is they are all done doing the testing. So basically, for the same mask, I built a lot of chips, maybe millions. Then during the testing phase, I can make each copy of these 1 million chips all different. So in the next couple of slides, I'm going to show you two technical techniques, how we can make this happen at the post-silicon stage. So this is a very simple digital circuit. You have an AND gate, and this is a NOR gate, and then this is an OR gate. So I have these two inputs, A and B, and then X and Y are the signals coming from these two gates, and then they feed into the OR gate here, and then produce a signal called F. And I can do a very simple analysis, which is what people call satisfiability domain here. So because of this X equals to B, and then Y is the NOR of A and B. So I can build a very simple truth table. For all the 4 input combinations of A and B, I see what will be the output of Y and what will be the output of X, so X and Y. And I take a look at this, and I observe one thing. So which means that X and Y, it cannot be 1 at the same time. Because of they have dependency, both depend on B. So this is something we say, the satisfiability domain here. Because X and Y cannot be 1 at the same time. So we write in this way. So now I consider a different gate. So this is the OR gate. It will be 0 if and only if both X and Y are 0. And this is the exclusive OR gate, which is very similar to the OR gate, except that in the case that when both X and Y are 1, it will also give you a 0. And basically this is the exclusive gate, and then sometimes people also call this one the difference. So as long as X and Y are different, I give you 1. If they are the same, I give you 0. So I highlighted the difference between the OR gate and exclusive OR gate. So at the input 1 and 1, they have otherwise they are the same. So now based on this, I can do some small magic here. So I consider this circuit. And what you see here is the difference between this to the left one, the original design, and the new design here is I have replaced this OR gate by the exclusive OR gate. And by just looking at the circuit, you see, these are different designs because the gates are different. But however, if you take a look at this table here, the only difference between this exclusive OR gate and the OR gate happens when both X and Y are 1. And we have analyzed here, because of their dependency on input A and B, X and Y, they can be 1 at the same time. Which means that in this particular case, these two circuits, although they look different, they are identical. So this is one way we can embed our signature, because basically by using either a OR gate or an exclusive OR gate, I can embed either a bit 1 or a bit 0. So this is how we can generate distinct copies, which we call fingerprints. So if I can identify n places of such conditions of chip, and for each place I can embed 1 bit, so eventually I can generate 2 to the power n distinct copies, which we call the fingerprinting copies. So this is extremely useful because I could design a universal gate which can be reconfigured either as a OR gate or exclusive. And this reconfiguration will be happened after silicon, after you fabricate it. And the second example here I give you here is again another type of dome tiers. This is one called observability dome tiers. So again, I start with a very simple circuit with 3 gates and 4 input signals, A, B, C, D. And X is AND of A and B, Y is OR of C and D. and X and Y will be added together to get the F. So I take a look at this one. I see if Y is 0, because of this is the AND gate. So when Y is 0, I don't really care what happens with X. So you change X to 1 or 0, it doesn't matter because F will be always 0 because of the fact that Y is 0. So this is the way we call it observability don't care. So when Y is 0, I cannot see the value of X is 1 or 0. So we will present it in this way. And now I see a different circuit. This is the one in yellow here. And see again, these two circuits are very simple. And however, I have one additional wire here, connecting this Y signal back to the AND gate, previously to the 2 input AND gate of A and B. Now this becomes a 3 input AND gate. And again, you will see this are the different circuits because you have different functionalities. This is a 3 input AND gate, this is a 2 input AND gate. So now let's do a one-step closer analysis here. So now we see the new signal X becomes AND of A, B, and Y. But however, if Y is 1, so X will be equal to A, B, and 1, which is the same as A, B. So it's the same as this functionality. So which means that if Y is 1, it doesn't matter. X generates whatever the same value as the previous circuit. And what happens if Y is 0? If Y is 0, I'm going to rent X to 0, no matter what is the value of A and B. So that is the point that it's going to make a difference from the previous circuit. Because the previous circuit, the X value has nothing to do with whether Y is 0 or not. But however, for the entire circuit, I only observe the output here. I don't really see the difference because when Y is 0, this is 0 anyway. It doesn't matter what you have here on the X. So as a conclusion, what we have here is no matter Y is 1 or 0, this circuit, functionality-wise, it is the same as the previous. So what we have seen here is with two different layouts, but they implement the same functionality. So which means that I can use this structure to represent two different circuits, which are doing exactly the same thing. And that is what we call the fingerprinting circuit. So there is a fingerprint bit, either one will fit. Another question here is how can you implement this in post-silicon? So what we do here is we are going to connect this wire before the silicon. Somewhere in the middle, we put a fuse. And then after the chip has been fabricated, during the test phase, and based on whether you want to embed a 0 or 1, you either leave this fuse on to implement in this version, or you burn the fuse. This can make this one disconnected, and then it will be the same thing as this. So this is the same thing as before. So if I can identify in different locations like this, I can generate that 2 to the power in different fingerprinted copies. So these two techniques, basically, they are post-silicon, they are extremely, low overhead, and they can be very, very practical. And the next thing I can just go very quickly. So this is probably, Dr. Gu has talked about, she has talked about it earlier today. And this is basically on what we call the physical unclonable function. And this is a very simple D flip-flop, and then this is the functionality of the D flip-flop. If the clear signal C is 0, I'm going to clear anything. If the clear signal is 1, and change the flip-flop content based on the need of the D input. So if I put a 0 here, and then after these 3 inverters, you'll have a 1 here, and then this entire thing will be set as 1, because there was 1 and 1. So now if I change this signal from 0 to 1, like I'm going up here. So eventually both these signals will go down from 1 to 0. However, what happens to the output here, to the flip-flop content? So this becomes interesting. Because of this functionality of the D flip-flop, and then also none of these inverters with these wires can be perfect. So these two signals may not arrive at C and D at exactly the same time. So what happens here is, if the top pass, if this one arrives earlier, so when this one changes from 1 to 0, this one remains as a 1. And then this content, because C is 1, D is 0, it will be changed to a 0. However, if the bottom one comes earlier, so this one comes to a 0 first, so it becomes a 0, and then I'm not going to care what you have here, because this is already a 0, so there's no change. So which basically tells me that because of these variations here, because of the timing, the delay variation, and if I change this signal from 0 to 1, the flip-flop content can be either 1 or 0. That depends on variations. So that is the bottom line about the physical path, the physical Unclonable function. And then there are some other memory-based path, and I'm going to go through here. So SRAM path, the lunge-based path, butterfly path, and then the flip-flop path. So how path can be used for authentication? We know path can do a lot of things, generate random numbers, and then store secret keys and all these things. So I'm going to talk about, this is how path can be used to authenticate a device or authenticate users. So this is the standard ring authenticated path. This is the standard arbiter path, which I assume that Dr. Hu has went through this morning. So I'm going to quickly go through here. It basically tells you that how this difference can be observed. So I'm going to mention 3 applications how path can be used for authentication. So the first one is I have a user Alice wants to verify a device or authenticate a device. So what Alice is going to do is, so Alice has some pair of response and challenges. So she's going to send a challenge or a task for the path device to do, and the device sends the response back to Alice. So what Alice will do is she's going to do a simple comparison. Compare whether the response is whatever she's expecting or not. If the response is correct, the chip has been authenticated. Otherwise, the chip is fake. So the key thing here is you will see, okay, so from the communication standpoint, so a Eve here, an eavesdrop attacker here in the middle, can see what is the challenge going to the device, and also see what is the response from the device. So what happens if people sit here and then trying to do some damage, do some malicious things. So the bottom line behind this is only the authenticated chip can generate the correct response. So that is because of the path property. So for the same procedure, if we reverse it, if we ask the device to send a challenge to the user, and then they put the check whatever she has in her database, and then provide a response back, this protocol can be used to authenticate the user as well. So this is a device and authenticate. So now we're talking about authenticate users, authenticate users. So now we try to talk about more authentications. So how we can use path to authenticate computations, particularly if you talk about the cloud computations. So if you have a dedicated device, and then you know that device is doing the computation. But now we move a lot of computation to the cloud. How can you know which server, which system is doing the computation? So in this case, if Alice wants to run the computation on a server's computer, and then she wants to make sure that it's the right result or the right server does work. And then a certificate based on the server's path can be added into the results. And then Alice can authenticate that path and then eventually authenticate the server and the result. And also this can be used to do the software licensing by binding the software to the hardware device. So basically, if Alice wants to send Bob a program, and then for example on Bob's cell phone, and then Alice doesn't want Bob to send this program to all his friends so they can play on their cell phone. So what Alice can do is, so she can for example change the program or make some copyright protected stuff, and that's going to be run only on Bob's cell phone. Because his cell phone is a hardware device, and that hardware device can have some emergency path type of feature. So it only can be authenticated for that particular device. So if Bob sends this app to his friends, but this can use itself, so that is not going for there. So this is the second piece of authentication where we use path. And the first one is we do a very basic digital design. And then the next thing is something more going down to the device. So this is a device which has been predicted more than 40 years ago. Professor Leon Hong, this is one of and I'm going to skip all these inclusions. Basically, the key feature about this device is this is a resistor, but however it has 2 stable resistance levels. We call it low resistance level and high resistance level. And then if you change the voltage, you would observe 2 stable states, and then they change following this bow tie shape. And it is a hypothetical assumption based on by analyzing these properties about the circuits, about the transistor. And after more than almost 35 years, so eventually people have successfully built the memristors. That was reported about 10 years ago by the HP lab. So they have successfully fabricated memory device called memristors. And then this is the one I call the bow tie shape. And then this is the one there when we do the real experiments. They show this is something very similar to what we see the theoretical prediction. Okay? And then since that time, there have been a lot of research on memristors, and also there are memristors for security. The key reason for memristor is for storage, because they consume no power. So what we do here is I'm going to skip all this security application of memristor, but focus on the authentication part. So people can build memristor-based path that can be used to authenticate device. That I'm going to skip here. And also people can use memristor to do computation, and then based on that, you can also authenticate the computation conducted by a particular memristor device. So what I'm going to report here is I'm going to tell you briefly about a couple of protocols we have developed for user authentication based on memristors. So the key idea behind these user authentication protocols is the concept called a pulse train. And a pulse train is just a sequence of very small pulses with the voltages. So when people study memristor for memories, they want the transition from low resistance level to high resistance level to be very, very quick. So the memory can get very fast access and fast read and write. So in our case, when we try to do authentication, we try to intentionally slow down this process. So we give a very short pulse, so you apply the voltage at very low voltage, and also a very short period of time. So when you see a 1 here, when you say up, that means I'm going to apply the voltage. When you see zeros at multiple cycles or pulses, that means I'm not going to apply voltage. And I do again, I stop, I do again, I stop probably 2 or 3 cycles. So this becomes a pulse train, and then basically just tells you that when and how many pulses you are going to charge or discharge the memristor. And then there are 2 phases, like most of these authentication protocols. So first we do a registration, and then Bob is going to choose a random sequence of the pulse, which is called a pulse train, and then he's going to apply this pulse train to a device that Alice owns. And then Alice is going to save the device response, so later on he can compare this response versus the response at the real time to authenticate Bob. And the verification phase happens at the real time, so by matching the stored response and the real time response. So how this happens? So during the registration here, so this is like the Bob's pulse train, and then after you apply this to a sequence of memristors here. So what we do is first we copy the state of what Bob has been doing here, and then we are going to apply the pulse train onto this one here. So this is at the real time. When we receive this, we're going to do this. Okay? So at the real time when we do this, we see, okay, so we start from memristor sequence here, and which are all initialized to be at the same initial state. So what we do now is we are going to apply what I received from Bob to this pulse train, to this sequence of memristors. And what we do now is we are going to see, okay, so based on this, when we apply this pulse train, which is supposed to be the same, so this looks like the password of Bob. So if we use the same password, apply this password to this set of memristors. And if everything this password is correct, and this memristor devices, they will be charged or discharged to exactly the same response that Alice has pre-stored here. So when we do a comparison, if we see they're the same, or up to certain levels because of noise or some other errors, for example, if I see 80% of the match, I assume this is a match. So in that case, Bob can be authenticated. So what happens you see here is, since I'm not going to use crypto to do this, so I'm basically used on the feature of memristor device to do this authentication. And finally, the last example I'm going to show you here is something we recently did early last year. This is called voltage over scaling based authentication, and it is used for device authentication. It can also be used for probably computation and also user authentication. So what is voltage over scaling? So voltage scaling is the method, or it is the procedure that you change the supply voltage or change the operating voltage for the system. And it has been developed since probably when we did it first time, it was 96. So the key reason of voltage scaling is trying to reduce power consumption, trying to save energy. Because you see this, the power based on the formula. If you reduce the voltage here, you save a lot of power consumption. But however, you cannot reduce the power to any low levels you want. So there's a critical voltage level. If you go beyond this critical voltage level, then you will introduce errors to the circuit. And most of these errors are introduced by the pass-through delay. So certain gates becomes so slow that it does not reach its final out at the right time. And this is a figure 1 shows the delay model. The error model due to the reduce of the voltage. And what we do here is we try to do this voltage overscaling. That is the one when you scale voltage close or below the critical voltage level. So what we did here is we consider, we try to design adders using hardware. And this is an image of people called forest or a whole bunch of trees. And this is another image called the snowflakes. And when you use your adder to superimpose these two images, or put one image on top of another, what you see here is what people call snow in the forest. So you have the trees and you have the snowflakes, and some of it is hidden by the trees and it's on top of the tree. So what we do here is we use different implementations of the adder. The same implementation of the adder, but on different chips. So what we do here is we consider this is the original image, and these are the two different images processed by two different chips. And they are identical in terms of the implementation of the adder. So what you see here is visually you can see both B and C are different from A. And the D basically shows you the pixel value, the pixel difference between every position of A and B. And this one shows the position, pixel difference between A and C. And our goal is trying to use this difference, this image map, to authenticate different devices. And you may say, okay, so I already see this difference here, and then a very dark point or spot means that there is a large difference in the pixel value at this position. And what will be, for example, if the false positive, if I categorize or misidentify B and C. So for you to see that, I compare the pixel values between B and C, and that shows you the last figure here. This shows you see a lot of black dots, which means the two different copies. If you compare them, you see a much bigger difference. So we're still doing more investigation on this, basically trying to see whether we can use this for authenticating different devices. So finally, let me conclude by saying, what is, in my opinion, what is the hardware's role in security? It is not just, it is something beyond authentication. So first, what we do secure, or we do any kind of applications or computations, we have to use hardware. For security, your crypto, they need hardware. And the crypto is just a whole bunch of algorithms. You need to implement in software, and the program to do that, and the software eventually will execute. And the second thing here is hardware, starting from probably 20 years ago when people started doing the power analysis attack, so it becomes a new hacking service.
So Gang, you have 5 minutes just to say?
Yeah, I will be done in about 3 minutes. So people are doing physical attacks to the device. They observe side channel information, trying to break the system, and they can install backdoors or hardware trojan to the hardware, and then use these trojans to steal the secrets. And finally, I'm going to mention this nowadays. Most of these hardware security folks were doing things is one of the things we call hardware security primitives. So these are something like the features, like the top. We use this to not just make your computation faster, but trying to provide a better security. Better in the sense that not always trying to be more secure, but sometimes more realistic, more practical, more resource friendly. And finally, to summarize this talk, because we talk about authentication for IoT applications, which are extremely resource constrained. So I'm going to mention 2 key points here, which we can take as the takeaways here. So first, if you do a hardware-based authentication, and the advantage over the crypto-based solution will be normally these are faster, and then they involve a much less computation cost. And then they are more secure in the sense that because of the physical facility, so people cannot access it, and it is harder to mess around. And however, I mentioned about this in here is, so they cannot provide the same level of security as the crypto-based solutions. But however, this is actually good for IoT devices, because we don't really need this 100% security. And the last point here is I showed you a lot of examples how hardware can be used for authentication of the device, of the data, of the computation, and of the users. We started from the people who have, the things people have been used for ages, the serial numbers. We go to the path. We go to the digital fingerprint for chip design, and then we talk about some emerging materials like the Memristor devices, and also we talk about some traditional techniques which people use for high performance or for low power design, like the voltage scale, which can also be turned for security applications. So this concludes my talk, and thank you very much for listening, and I hope in the future I can see you guys in person at some time. Thank you.
Okay, so do we have any questions for Professor Koo? Time for one quick question. Yeah, do you want to come over, or because I think he won't hear you from there. That's okay. Not to put you on the spot, and then he can see you too.
Hi. Thank you very much for your talk. So you were talking about using puffs for authentication. I was wondering, have you thought about, or how do you prevent man-in-the-middle attacks? So if you have a person in between Alice and Bob, how do you detect whether there's someone in between the communication or not?
So that is an excellent question. So let me go back to that slide again. And so the question here is, because of this communication here, so how can we make sure, Alice received this challenge goes to the right person, and then the response comes back from the right person. And that is the standard question for this communication. And what people use here is, we try to use this thing called the time of arrival. So if this is the authenticated device, so I send it to him, and then he's going to respond right away. So if it got a delay from different channels, and then I can probably detect from that. And also this is the way people use to prevent this, whatever you do, the machine learning attacks. So you have to learn something, on the spot, so your response will be not as quick as this device. And another feature which people have been studying recently here is they are trying to do another, for example, position-aware challenge, or in some sense that is the word people call attestation. So you want to authenticate this is the right device at the right situation to do all these things. So for that, if you really have a person standing in the middle here, intercept all the signals with no overhead of timing, then it's not possible to detect it. And one way to do that is you can do encryption, which is something what I try to avoid.
Okay, thank you.
Thank you.
Okay, so in the interest of keeping us to time, can I just thank the speaker again, everyone? If anyone has any further questions, perhaps.